240 volt loads and Edison 3-wire. Let's just take a look at a brief example about how we can utilize this type of load with a 3-wire distribution and how we handle some of the calculations. So here is our classic 3-wire Edison with the conductor resistance and the loads, nondescript box of loads, whatever that is. There we go. These here, two loads, would be considered 120 volt loads. So this would be a 120 volt load and a 120 volt load. And what I mean is that they would be rated to operate at a maximum of 120. If we were to continue this diagram all the way out here, my third load, this one would be a 240 volt load. So this one would be rated to handle a full 240 volts. And so if we wanted to calculate any of the values within it, we would go through the same process as what we've done before in previous Edison 3-wire. So although it's rated for 240, is it actually going to see 240 volts? No, probably not. So let's add in some values. I'm going to say 0.1 ohms is going to be the value of resistance for each one of the conductors that are present in the diagram. And then I'm going to put in a few values of current, 10 amps, 20 amps, 15 amps. By doing that, now we can go through and determine where the current values will be and what the voltage is across each one of our individual loads. So I'm going to apply a polarity to my Edison 3-wire source first. They have to be connected in series. And then what I'm going to do is start indicating the value of current on each one of my lines. So 10 amps, 10 amps, 20 amps, 20 amps, 15 amps, 15 amps, 15 and 10 gives me 25 amps. And of course, on the bottom, 15 amps and 20 amps gives me 35 amps. The difference between the two, 25 and 35, is 10 amps, and I know that that would have to be on the neutral. So right off, I'm going to apply a polarity to all of these individual resistance values. And now I can work out the value of current on the neutral. It's 10 amps, and we can see by the direction of the arrow, 10 amps enters the junction, 20 leaves, which means another 10 must be entering the junction, which would mean the polarity of that particular portion of the circuit, negative, would be on the left. So for load number one, load one would have a voltage. Well, we'd need to work out the individual voltage drops, right? So let me use red, and we'll say 2.5 volts, 1 volt, 3.5 volts, because each one of these has a resistance of 0.1 ohms. All right, so first one, load one. Voltage, load one, is equal to, going through a loop inside here, this is a closed loop, so 120 minus 2.5. We come along the bottom, plus 1. So 120 minus 2.5 plus 1 equals 118.5. Voltage load 2, positive 120, going through a closed loop, negative 1. Coming around the back side here, negative 3.5. So 120 minus 1 minus 3.5 equals 115.5. For the last load, you really have a choice. So voltage of load 3. The voltage of load 3 you could calculate by doing a complete perimeter run along the circuit, as in the external exterior lines of the circuit. We could do that. And in that case, it would be positive 120 and positive 120. We would continue along the outside, negative 2.5, negative 1.5, And along the bottom, obviously, the exact same thing. So negative 1.5 and negative 3.5. This would give us a grand total then. If I enter it into my calculator, that would be a total of, I'm going to go over here, 240 volts minus 2.5 minus 1.5 minus 1.5 minus 3.5, giving me a voltage across that load 3, or the 240 volt rated load, of 231 volts. If you then wanted to go further and work out what the calculated value or voltage would be across each of these individual loads with the neutral broken, the same process would still be followed as in the original Edison 3-wire. We would have to work out the resistance of each of these three, and from there we would build ourselves a new circuit. Remember, the circuit is going to look a little bit different, and just to follow this one all the way through, we may as well complete it all the way. So next step I'm going to do is work out the resistance for us. So the resistance, and I'm just going to go on to a new sheet of paper so that we have something clean to work from. The resistance, I'm just going to sketch very briefly here what the original circuit was. Like that. Beautiful sketch. Oh, look at that. Okay, so that's load 3, load 1, load 2. We'll put a little box around them. Okay, so first things first, let's work out what the resistance is. This one here was 118.5 volts, and it had a current flowing through it of 10 amps. This one here had a voltage of 115.5 volts and a current flowing through it of 20 amps. And finally, this one had a voltage of 231 volts and a current of 15 amps. What that means is I can use Ohm's law to calculate the value of resistance. As the French say, I'm sure, I don't know, I've never been to France. So down here, we would then do resistance. R is equal to E over I, which means that load 1, load 2, load 3, right? Because of 1, 2, and 3. Oops, that's really crappy 3. There we go. So load 1, 118.5 divided by 10 gives me 11.85 ohms. Load 2, 115.5 divided by 20, 5.775 ohms. And load 3, 231 divided by 15 gives me 15.4 ohms. And so what this then leads to is if we have a broken neutral condition, well, broken neutral means that we now have to use these ohmic values in order to build ourselves a new circuit. So not too terribly difficult, but certainly time consuming. It is time consuming. So let's see what our new circuit's gonna then look like. Well, our new circuit with a broken neutral is essentially a 240 volt source. And that 240 volt source has this. Should look somewhat familiar, like this weird combination circuit, right? Combination circuit is really what we have here. And so the ohmic values for each one of these are 0.1 ohms, 11.85 ohms, 5.775 ohms, 0.1 ohms, 0.1 ohms, 0.1 ohms, and finally 15.4 ohms. Well, next step, we're going to have to, remember, combine the resistances. We want to get total current on this. So in order for us to accomplish that, I'm going to have to break this down and make it into a single equivalent chunk of resistance. And so what we're going to do is we're going to take this and we're going to combine all of these first. Okay, so what I'm going to do is this. 240 volt resistor, 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 resistor. So what we're left with is these 1, 2, 3 combined to give me this one here. So 0.1 plus 15.4 plus 0.1. Well, that would be 15.6. So 15.6 ohms, right? And these 4 would remain the same, wouldn't they? So that would mean that we would have to yet combine them once more. So next step, what would that be? Well, I'm going to go and combine them, and I'm going to have to slide this up a little bit. .6 ohms. Takes a lot of space to do these calculations. So now what we're going to do is we're going to combine these two here. And when I do that, we're left with a circuit that looks like this. So there's my 240 volts. And I have 15.6 ohms here. Looks good. And what about these two here? Well, these two were 11.85 ohms and 5.775 ohms. So that means that when I combine them together, I simply add them. So I get 17.625 ohms of resistance. And what would be the final step then? Well, we would probably want to take these values and combine them so that we have a parallel combination of those two. So remember, what are we doing with all this? We're trying to get the total resistance of this entire circuit. So new drawing, 240 volt. This is what we're going to be left with. These two values here are still 0.1 ohms. And 0.1 ohms and this final resistor here, what's this one? Well, it's the parallel addition of both of those. So that would mean that we have to take our original value. So I'm just going to put it in my calculator, 17.625 to the -1 plus, well, let me enter that again. 17.625 -1 plus 15.6 -1 bracket -1. I get 8.27 ohms. .275 ohms. So, oh man, final diagram would look kind of like this, wouldn't it? We'd have down here, we would have, let me just line these all up. There we go. Excellent. What we would have is a total combined resistance that is equivalent to 0.1 plus 8.275 plus 0.1. So our final diagram looks like this. 240 volts. And that would be 8.475 ohms. Oh, you're shaking your head going, why on earth do we do this? Well, we did it so that we could work out the calculated value of the current, the total current that's going to be in the circuit. Man, that's a lot of work. So what's 240 divided by 8.475? 28.31 amps. 28.31 amps. Why would we want to know that? Oh, great question. We'd want to know that because what I'm going to do is use this value of current and work my way back up and calculate what voltage is across each one of my loads. So let's take this up here, 28.31 amps. Well, let's sketch it here, 28.31. It's a series circuit. Let's calculate the voltage across this 8.275 ohm resistor. That would be simply Ohm's law. E is equal to I times R. So 28.31 times 8.275 gives me a voltage across this particular item of exactly 234.26 volts. Okay, well that's good. Let's move back up the chain then, because really what we need to know is the voltage across each one of our individual loads that we've had. So 234.26, that's actually the voltage from this point to this point. So both of these resistors have the same voltage, 234.26 volts. That would be from here to here. So both of them, this chunk of resistance and this one, both have the same voltage. Well, let's calculate the current that would flow through this particular branch. So I'm going to take my voltage and divide it by the resistance. 234.26 divided by 17.625 gives me a current value of 13.291 amps. Okay. Well, let's keep moving all the way up until we get to our original diagram. Why did I even do that? Well, I did that, 13.291, so that we could work out the voltage of our two loads. What about this one? Well, let's work out the current for this one also. 234.26 divided by 15.6 gives me 15.01 amps. So 15.01 amps. All right, so next step, let's calculate the voltage across our final couple of loads. We have 15.01 amps, 13.291 amps. So if I want to work out the voltage across these two loads here, I need to use the current that flows through these two, right? If I want to work out the voltage across this one, I need to use the current that's flowing through this series branch. So I utilize the current to get my final answers up here. So let's do the first two loads, work out the voltage across them. The voltage of my first load here is the current multiplied by the resistance. 13.291 multiplied by 11.85. 157.4 volts. What about the voltage across this one? Take the current, multiply it out. 13.291 times 5.775 gives me 76.7 volts. And then finally, the current multiplied by the resistance. 15.01 times 15.4 equals 231.1 volt. So the question would then be asked, which of the loads would fry? And the answer is that only load 1 would fry. Load 1 is overvoltaged. It's really only meant to handle a maximum of 120 volts. We saw back here that with an intact neutral, it was able to carry or able to handle 118.5 due to the line drop. As soon as we broke the neutral, the voltage went up. And so whatever that load was is getting over voltage, and likely it will fail, catch fire and explode, and death and mayhem will follow. This down here, well, this one is under voltage, so not much will happen. Whatever it is will cease to operate or be dimly lit. And then finally, what about the 240 volt load, or the load that was rated for the full 240 volts of my single phase system? Well, you'll notice the voltage didn't change too much there, did it? the voltage remained pretty much untouched. And so the 240 volt load would continue to operate. So what's the significance? Well, when you have an open neutral situation, any baseboard heaters in a house are probably going to be fine. Unfortunately, that kind of sucks because those are the cheapest objects in your house. Depending on what things are turned on or off in the house, your TV, your computer, all the other fancy things get fried, depending on what circuits they happen to be connected in. So, a good application of an open neutral.